We're going to talk more today about testing, and so we'll keep going through the testing.r script, talking about common task with omics data where you have thousands of features and you want to find the subset of features that are different between comparison groups. That could be 2 comparison groups like treatment and control, or it could be 5 comparison groups if you had 5 different tumor types, for example. But we want to go gene 1, is this worth looking at? Does it seem to be different in its activity level comparing the different groups, or protein 1 or peptide 1 or SNP 1 or whatever? So last time we did the first little bit of the simulation, which was just to generate some fake numbers, 1,000 features, and 10 observations in each of 2 comparison groups. And we started by doing this in a way where there were no interesting features. All 1,000 of them have no differences between the 2 comparison groups because we used the same mean when simulating the data. So if we go through and do testing, we expect to see something specific for the distribution of p-values. We could do, in this case, just a 2-sample t-test because we only have 2 groups. So this loops through computing a t-test and storing the p-value. And we looked at the histogram of p-values and said it looks flat, uniform between 0 and 1. That's what you expect. If the null hypothesis is true and you do a hypothesis test, you expect your p-value to be uniformly distributed between 0 and 1. So if your p-value threshold is 0.05, for example, and you're trying to control the probability of making a type 1 error at 0.05, you would reject if your p-value is less than 0.05. And what's the probability that you see a p-value less than 0.05 if the null hypothesis is true? If the p-value distribution is uniform, between 0 and 1, then this is the distribution of p-values. Total area in that region, it's the total area under that curve. What's the total area under any probability distribution? Has to be 1. So since it's just a square, what's the probability of seeing a p-value less than 0.5, say? This would be 0.5. What's the probability of seeing a p-value less than 0.25? 0.25, because the area of that rectangle would be 0.25. So here's 0.05. Probability of seeing a p-value less than 0.05 if the null is true. So this would be like a false discovery. You didn't want a small p-value because the null hypothesis is true. But just by chance, 5% of the time, you will get one. We then made the data have some interesting features. We took the first 30% and we created some differential expression. We made it so that the mean in the first group was not the same as the mean in the second group. And that gave us a picture like this of the p-values. And we said that looks like a mixture of 2 distributions. We had this kind of thing, and we said that this could be thought of as a mixture. Let's say there's pi0 proportion of all the features that are not interesting, which means whatever's left, 1 over pi0, are interesting. Interesting features will tend to give us small p-values because they are differentially expressed. The means in the 2 groups that we're comparing are not the same. Okay, we've seen that. Now let's look at this. We just computed those p-values. We have 1,000 p-values. 300 of them, the first 300, correspond to features for which there is a difference between the comparison groups. Suppose we just have the p-values. What proportion were less than 0.05? We did 1,000 hypothesis tests, and we decided we're going to filter out, select the features that had a p-value less than 0.05. We would be left with 169 features. So that would be our subset that we would look through and try to investigate further. Let's see. So think about what you can say about those 169 features. The biologist collaborator gives you the spreadsheet full of all the data. You go through, do your tests, come up with 169 p-values less than 0.05. You hand those over to your collaborator, and you say, I think these are the interesting ones. And he or she asks, how confident are you in them? Are you really confident that these 169 are interesting, or are you just a little confident? What would you say? What you could say at this point is, I used a p-value threshold of 0.05. What does that mean? That means the probability that I would make a false pickup if the null is true is 0.05. But we just did it 1,000 times. We just did that 1,000 times. Every time we did a test, the probability of making a type 1 error was 0.05. So I can't say something like I'm 95% confident in these 169. If I did a single test and rejected if the p-value was less than 0.05, I could say I'm 95% confident that the groups differ in terms of their mean. But having done multiple tests, at the end of the day, I don't get to say something straightforward about type 1 error because we did multiple tests. And every time you do a test, you accumulate more and more chances of making errors. So we would like to be able to say, here's my 169 features that I think are interesting, and I am 95% confident in that. I'd like to be able to say something like that. But with just a p-value, we can't. So that's why people do one of two things when they're doing testing with omics data. They either adjust the p-values by inflating them to account for the fact that you're doing multiple tests. And then when you do your, when you look at the adjusted p-values, you would do this again. Find how many features had adjusted p-values less than 0.05. If we adjust for this multiple testing thing, I said we're going to inflate the p-values. So if I did that, would this number be bigger or less than or equal to 169, do you think? It'll be less than, because I had to increase the stringency of my criterion, which makes sense. If you don't adjust for multiple testing, you're making errors more often than you claim you are. So in order to guard against that, we have to increase the p-values, which decreases the evidence for statistical significance. That's one thing we could do. Do some adjustment to the p-values, get a smaller number of features, and say what I'd get to say in that case is the probability that I made any type 1 errors in this list is 0.05. The probability I made any type 1 errors. In the context of bioinformatics, when you have lots of features, chances are you're okay with making a false discovery. You want a list of 100 features, say. It's okay if there's a few in there, just don't put too many. So arguably, adjusting the p-values by inflating them is more stringent than you want it to be. The false discovery rate, one sec, is an alternative way. Instead of type 1 error stuff, you talk about a different error measure called a false discovery rate, and I'll show you it in a second. It allows you to do that balance thing. I want a list of differentially expressed features, and I want to be able to say I expect no more than, say, 5% of that list of 169 as being false discoveries. That way you've kind of balanced. I'm giving you 169 features. There may be some mistakes, but I don't expect more than 5% of them in that list to be mistakes. Question? Just adjusting the p-values. Suppose you did 5 tests. I have a drug, does it cure cancer? I have 5 configurations of the same drug, and I'm going to give that drug to, collect a sample of people, and I'm going to do a test. Is this configuration of the drug better than control? Now, is that configuration better than control? Do it 5 times. I have 5 p-values. Suppose I took the smallest p-value, and if it was less than 0.05, I said the drug worked. That's an error. I don't want to, that's kind of cheating, because the overall error probability is bigger than 0.05 now. So what I'm talking about is taking those 5 p-values and making them bigger, which makes it harder on you to find statistical significance. That's how you inflate the p-values to guard against this issue. So literally increasing the p-values. The simplest way to increase the p-values is called the Bonferroni Correction, and all that does is multiply the p-values by the number of tests you did. So if we did 5 tests, I would take all the p-values, multiply by 5. So if one of them was 0.02, now it's 0.1. It was, I have less evidence. I've inflated, I've kind of compensated for doing multiple tests. You would do.
Don't you set? You don't. Like when you do Bonferroni, you don't multiply. You just set your significance level differently by.
It's equivalent. You can either divide the 0.05 by a number to make it smaller, or you can inflate the p-values.
Do you? I feel like you. So I do this when I do GWAS.
Mm-hmm.
You don't actually delete the ones like that 800. You kind of just set them to 1, so the p-value to 1, so they just kind of baseline and everything else goes above it. Is that kind of what you're doing?
If you, say, did the Bonferroni thing and you multiplied all your p-values by 1,000 in this case. In fact, let's do that. P adjusted is p-vals times 1,000. That's Bonferroni adjusted p-values. Now some of them are bigger than 1, so I would cap it at 1. I would just do p adjust wherever p adjust is bigger than 1, make it a 1. You're not going to look at those anyway, the ones that are way up there. You're only going to look at the small ones. So how many of my adjusted p-values are less than 0.05? It's only 7. But I can say about these 7, here's my 7, and the probability, the procedure I just used corresponds to a type 1 error rate of 0.05. So the probability that if you were to do this again, go out and get a sample of 1,000 features with 20 individuals in 2 groups and do a 2-sample t-test, the probability that you would make any type 1 errors in constructing this list is 0.05. So that's a stringent, precise statistical statement, but it's maybe more stringent than we want. Yes?
It seems very subjective. You don't exactly know if you're being too stringent or lack of stringent.
Mm-hmm.
Way of determining if you are going overboard or if you're not.
I'll show you a picture that you can make, a diagnostic picture, so that you don't have to decide. In fact, when I do this, I don't decide ahead of time. I make a picture and I look at the trade-off. As I make the stringency more and more and more, what's the trade-off in terms of how many features I get? And often, if you make the picture, you can see increasing stringency up here gets me lots of new features, and then beyond that point, I don't get much more. So I'm gonna draw my threshold at 0.07 or something. Here's my 200 features, false discovery rate 0.07, and I picked the 0.07 based on the picture. I'll show you a picture. So I'm trying to motivate false discovery rate. P-values, that's where everybody started with bioinformatics data statistical analysis, but then they ran into these issues. Let me do a couple of other calculations here. Let's do this. This is going to tabulate what proportion of the actual differentially expressed features, those were the first 300, what proportion of them had p-values less than 0.05. 134. There were 300, and 134 of them showed up in our list, this first list, 169. So 134 out of those 169 are true positives. You don't know that in practice, though. In practice, all you know is your p-values. You can make this, you can do this calculation, but you don't know which are the real and which are the false discoveries. We're playing pretend with a simulation so we can print this out. So that means of the 169, not all of them belong in there, right? Usually false discovery rate is used when you're doing like hundreds of tests. If you're doing if it's closer to a classical kind of statistical application where it's 5 tests, something like that, I would recommend just do a p-value adjustment. Stay with the type 1 error rate. It's fine. The false discovery rate is most useful when you are doing lots of tests. What proportion of the null features, by null features I mean features for which the null hypothesis is true, everybody but the first 300, what proportion of them showed up in our list? It was 35. So 134 plus 35 is our 169. So out of the 169, what proportion were false discoveries? It would be 35 divided by 169. The false discovery rate for this collection of 169 selected features is 20%. That's a false discovery rate. It would be, if we estimated it, we just computed it using what we know about the simulation. But in practice, we wouldn't be able to compute this directly. We have to estimate it. And the way we'll estimate it, and I'll show you momentarily, could be with what's called a Q-value, which is basically the false discovery rate corresponding to that list of selected features. So in this case, we used p-value thresholds of 0.05. That seems stringent, that's a small p-value. And we got 169 features. But we don't know anything about what proportion of those 169 features are false ones. Just based on the p-value, we don't get to say that. And in fact, that proportion is actually kind of high. 20%, 21% of those are null features. False discovery rate stuff, we're going to talk about when we don't have a simulation where I know these numbers, where I won't know that number in practice. We can still estimate this. So if you do false discovery rates or you compute Q-values, you're going to be estimating this. I did 2 sample t-tests. I got all these p-values. I ordered by the p-values, and I picked the top 100. FDR with a hat on top, my estimated FDR is such and such. If I picked the top 200, my FDR would be so-and-so. That's the picture that we're going to make, FDR versus number of features picked. Mm-hmm. Okay, let's go and talk about that. This is a paper that's on eCampus. It's story 03. And this was from Proceedings of the National Academy of Sciences. So it's readable. And it's a good presentation of what FDR is about. So let's check out this table. We have M features generally. In our simulation, it was 1,000. And some of those features are null features. They are not interesting. They are not different in terms of their mean expression level between comparison groups. And the other ones are interesting. We say the alternative hypothesis is true. Of the features that are null, we will potentially call some of them significant. Select them. Call the number of null features that we call significant capital F, like a false discovery. Call the number of alternatives that we correctly call significant, capital T, for true discovery. And call M0 the number of features for which the null is true. So out of our M features, there's M0 uninteresting ones, but we don't know what M0 is. We do know how many we call significant. We go through and do a t-test or an f-test or a regression model and we get p-values. You pick a threshold, 0.05 or something, that tells me what S is. That's the total number out of your M features that you've selected. But we don't know these numbers and we don't know that number. Turns out we can estimate them. So here is the definition of the false discovery rate. False discovery rate is the expected value. So expected value is a probability calculation. It's like a mean. The mean average value of number of false discoveries divided by total number of discoveries. Expected value of F over S. So if we could, you tell me what S is. You did your 2 sample t-tests, got your p-values, and suppose we pick out 100, the top 100 features. Then I want to estimate the FDR corresponding to that. Here's 100 features. The estimated FDR, let's put a hat on this, is equal to an estimate of this. S is known, F is not known, so I need to estimate F in order to estimate the FDR. Here's how we're going to do it. You tell me the p-value threshold you're going to use. Do 2 sample t-tests, get the p-values, and let's use a p-value threshold of 0.05. That's what this T is. The FDR is a function of the threshold you use, because if you use a more stringent threshold, you're going to have a lower FDR. So the FDR as a function of T, we can estimate it. It's approximately equal to the expected value of F divided by the expected value of S. The expected value of S, I can estimate with just S. S is the number I just computed. If the p-value is 0.05, that's the threshold. How many of them had p-values less than 0.05? So it boils down to estimating this thing, this numerator. What is my estimate of the number of null features in my data? By the way, if you think back to this picture, we take our M p-values, we make the histogram, we see that. And we said that this could be thought of as a mixture of a flat distribution for the null features and something like this for the alternative features. So what we're going to do is kind of decompose this picture. We're not going to know what pi 0 is or which specific features go into each of these two. But we can look at this and say, I believe that's a mixture of one of these and one of those. So if we could estimate pi 0, if you could look at this picture and say, what's an estimate of the proportion of the two contributors? They have to add together to integrate to one. It has to be like a probability. So it can be done. We can estimate this quantity, which means I have an estimate. I can plug that in to get an estimate of the false discovery rate. So here's where we are. I want to estimate the FDR for a given thresholding rule. To do that, I need to estimate this numerator. Okay. So for a given p-value threshold t, like 0.05, we're going to reject or select a feature if it has a p-value less than 0.05. What is the probability among the null features? What is the probability of getting a p-value less than 0.05? We answered this already. Among the null features, what's the distribution of p-values? 0 to 1 in uniform, right? So the probability of getting a p-value for one of those null features that's less than, say, 0.05 is, we said it earlier, 0.05. So each of the null features is either going to be called significant or not. Capital F is the number of null features that were called significant. Each one of them has probability t of being called significant, because t is the p-value threshold. It could be 0.05, could be 0.01. But the probability that any one null feature has a p-value below that threshold is t. So the expected value of this quantity, this is, if you're familiar with the lingo, this is a binomial random variable. And the expected value of a binomial random variable is the number of trials times the common probability of success. M times t, M0 times t. The probability that this one null feature gets selected is just t, the probability that you get a null p-value less than t. And then there's M0 of those null features. So the expected total number of selected null features is the number of them times the probability that any one of them gets selected. So the point now is that we're trying to estimate this. The thing we're focusing on is the numerator. And we just wrote the numerator as M0 times t. T we know, that's the p-value threshold. I can choose that to be 0.01, 0.05, whatever. M0 we don't know. Here's that pi 0 from the whiteboard that we had. Pi 0 is defined as M0 divided by M. So pi 0 is just the proportion of your features that are uninteresting. The proportion of features that are null. And then here's what we can do. Where's the picture? Doesn't have a picture. Here's what we can do. Here's a histogram of p-values. We've got a mixture of differentially expressed and non-differentially expressed features. Suppose we, let me draw another picture real quick. Okay. Suppose this was our p-value histogram, uniform between 0 and 1. What would that tell you? You did a bioinformatics experiment, got m by n numbers, and you did a two-sample t-test to compare your two groups. You did got the p-values, did a histogram of the p-values, and you saw that. Is there, what can you say about signal, structure, anything interesting in your data set? There's nothing really in your data set. If you see a p-value histogram like this, there are no differences. So if you're comparing treatment to control or 5 different diets or something, and you see that, there's not much there. If you did see this, What's that?
What's this? What's that?
If you did, let's suppose you did a gene expression microarray experiment. You have 10 microarrays for cancer people, 10 microarrays for healthy people. You have 15,000 genes on the arrays. You go gene by gene and do a 2-sample t-test and get a p-value. You make a histogram of your p-values, and it looks like that. It looks flat. If that were my picture, I'd go to my collaborator and say, on the right, yes, that. If that were my picture, I would take that to the biology collaborator and I would say, there's nothing going on in your data. There is no interesting story in your data. Most of the time, it will look like that, which indicates there are some interesting features. There's a subset of your features that appear to be interesting. Okay. Okay. If this one was the case, then the height of the histogram, or the height of this distribution, would be 1. Because that's uniform 0, 1. It has to be good. Between 0, 1 here, between 0, 1 vertically. Suppose that we add in some differentially expressed features. So I'm going to take this guy, and I'm going to try to fit in. I want to take some differentially expressed features, and I want to mix them in with non-differentially expressed features. So suppose there's 1,000 features, and 700 of them have that one, 300 of them have that one. If you mix all those together, what's going to happen to this height? So if you mix these together into that, is that height going to be bigger or smaller than that height, do you think? You already said it's going to be smaller because if you just looked at that as a distribution, it has to integrate to 1. That's like a probability distribution for the p-values for the differentially expressed features. This one has to integrate to 1. This has to integrate to 1. If you take two things that integrate to 1 and just stick them on top of each other, they're not going to integrate to 1. So what has to happen is they have to be scaled so that the whole thing, this whole thing, integrates to 1. And what that means is that this flat part, the flat part, has to be pushed down to accommodate these extra ones. So suppose we are looking at a picture like this. I know if there's no signal, the height of the flat part should be 1. So let's suppose 1 is right here in this case. The height of the flat part is quite a bit lower than 1. That says there is signal. It's the flat part is having to share space with differentially expressed features. And it turns out that the actual height of this thing is an estimate of that pi 0. If all the features are null, the proportion of features that are null is 1. If they're having to share space with some differentially expressed features, it turns out that the flat part goes down, and where it ends up is a bona fide estimate of pi 0. And that's the only missing piece that we have to estimate FDR. So what happens? Well, one way that FDRs are computed, Q-value way, is to look at our histogram of p-values and essentially ask, what's the height of the flat part? There's more or less sophisticated ways to do that. One way would just be to go out visually to where it looks like it's flat and compute like the average height of the histogram bins out there. A more sophisticated way would be to fit a smooth curve. What just happened? So suppose this is our picture, and suppose we fit a smooth curve to this thing. You expect a pattern like that, peak at the left and then going down to flatness. So if you fit a smooth curve, you use all the data to estimate the height over here. So you could take the estimated curve and take the fitted value way over on the right as your estimate of pi 0. That's the idea. Let's go back to the paper. Here's our estimate of the false discovery rate. You tell me the threshold that you're going to consider for the p-values. Then the estimate of the false discovery rate is my estimate of the number of false positives divided by the number of total positives. And now my estimate of the number of false positives, that capital F of t, we said the expected value of f of t is m0 times t. m0 is the number of null features. T is the probability that any one of them has a p-value less than t. And m0 we used to define this quantity pi 0. Pi 0 is the proportion of features that are null. So this here, up on the previous page, was m0 times t in the numerator. And all we've done is replace m0 by m times pi 0 hat. M times pi 0, whatever the proportion of null features is, m times pi 0 would be m0.
So on your histogram, pi hat is basically just y of your equation at 1 and x equals 1.
In this picture, if we fit a smooth curve and we said, like, the p-values, let's say p is some function of the, let's say, pi is some function of the threshold that's used, p-value threshold, then we could estimate f to get a hat on it, and then pi 0 hat would be f hat of 1. So this is how you can estimate a false discovery rate. 5,000 tests for t equal to 0.05. How many p-values were less than 0.05 in the denominator? M would be 5,000, t would be 0.05, and pi 0 hat, we would estimate it from that histogram of p-values. Put it all together, you get a number between 0 and 1. And it's an estimate of this quantity up here. The expected proportion of the tests that came out significant, the expected proportion of your list of selected features that are false positives. Okay. There's a number that's associated with the false discovery rate that's analogous to a p-value. So a p-value, I think you guys know how to interpret a p-value. The formal definition of a p-value is the minimum type 1 error rate that can be achieved when calling a statistic statistically significant. It's kind of a technical definition. Roughly speaking, it's the type 1 error rate that would apply if you were to reject your null hypothesis. there is an analog for the false discovery rate. It's called the Q value. It's like switching the P backwards. And it is defined as the minimum FDR achievable when calling a particular feature significant. Roughly speaking, that's going to be just the FDR. So what I will show you in a second is we can go now feature by feature, 5,000 features, do a 2-sample t-test, get p-values, convert those p-values to a false discovery rate. So if I try at a p-value threshold of 0.05 and I get 169 features, I can estimate the false discovery rate for that 169. If I did that, then here's my 169, and I'm 95% confident in that list of 169. That's useful because now you know how confident we can be in them, but that did not give you a number for each feature. It only gave you one number for all of them together. P-values are nice because they give you a number for each test you do, a specific number. Not just whether it was less than 0.05, but the specific number. Was it almost zero, tiny, or was it 0.049? Would be interesting to know, in addition to yes or no, was it less than 0.049 or less than 0.05? So in the FDR context, there's something called a Q value, and this is what we assign this to every feature. So you take your p-values, convert them to an FDR, and then with the FDR, you can back into a Q value and give that to every feature. And it will turn out that every feature that has a Q value less than, say, 0.05, if you pick those into your list, you will get to say the false discovery rate for that resulting list is 0.05. So for whatever p-value threshold you used, that corresponds to a false discovery rate. And all the features that got selected into your list would have Q values less than whatever the false discovery rate is. So if we did our p-values, translated to FDR, and got an FDR of 0.1 maybe. So we got 5,000 features, we did a test for every one of them, and 200 features came out with p-value less than 0.01. We estimate the FDR for that 200 features to be 0.1, say. We can then go compute these Q values, and for all the features that are going to be selected as part of that list, their Q values will be less than 0.1, that FDR estimate. It will help, I think, to see this in action with a real data set. Yeah, you're getting a number so that you're getting a number for every feature so that the ones that are going to be selected all have numbers that are less than the FDR. You are scaling things. You're getting a number for every feature that's been scaled so that only the ones that have Q values less than that FDR are going into your list. Okay. Let's look at these pictures and answer that. Here are some diagnostic pictures that you can make when you're doing false discovery rate stuff. Here's one picture. It's the p-values this is for a real data set. Compute p-values for all the features and then convert them to Q values. And here's a picture of them. They don't equal, and you can have Q values less than the p-values or Q values bigger than the p-values. It's a little bit confusing, but the key is when we do false discovery rate stuff, we're doing something different from p-value stuff. P-values are engineered to work with type 1 error rate. Q values are engineered to work with false discovery rate. And those are two different error quantities. So just because you do not get to say my Q values are all going to be bigger than my P values, or vice versa. Sometimes it can go either way. If you think FDR is appropriate, you did lots of tests, don't worry about the P values, what they are. Look at the Q values, because that's what you can interpret in terms of false discovery rates. So it may well be that you had a P value of 0.04 and a corresponding Q value of 0.1. Then if you wanted a false discovery rate of, say, 0.05, you wouldn't pick that one. Here's a picture that gets towards Mitchell's question about choosing, like, what should my FDR threshold be, say. This puts, for all my thousands of features, I have a Q value. Plot the Q values versus how many genes or features do I get for that FDR. So if you follow the trajectory, a Q value or an FDR threshold of 0.02 would get me about 30 features. If I increase that a little bit, I'm allowing for some more errors, but in this particular region, increasing a little bit gets me a lot of extra features. So moving the FDR up to 0.025 or so, I get 80. I get an extra 50 features. Beyond that, it's kind of linear. So I'm trading off kind of equally errors for extra finds. So I might, with this picture, say I'm happy right here. I can tolerate an FDR of 0.025. That seems like a good trade-off, a good balance between errors and how many actual interesting things I get to investigate further. So a picture like this allows you to decide kind of on the fly what to pick out. Let me show you a quick calculation.
So could we make that, can we make that C graph with the simulation we just did?
Mm-hmm. I will. Yeah, let's do it.
Isn't that the one you look at to see if, like, using Bonferroni is more, like, because if it's following that trend and you decide to go from 0.2 to 0.25 and you get the same number of significance as you would with Bonferroni, you're not really helping yourself by doing that.
Yeah.
So you kind of want to compare both of them.
The false discovery rate can generally be relied on to get you more than any type 1 error based approach. FDR, type 1 error is more conservative, more stringent. I want to guard against making any errors in my list, whereas the FDR is saying we're going to allow some errors but not too many. So it's going to get you more. I would say don't worry about p-values. If you're doing thousands of tests, just look at the false discovery rate.
Because when I talk to the guys like that, like Alex with Gavin, he says never use the adjusted p-values. Get things like GWAS.
Did he?
Always provide your regular p-values and don't worry about it.
Yeah, you won't get as much stuff, but I mean, the p-values will be smaller, so you'll get more, but included in that more is going to be more false positives than you expect. And you don't know, you don't have a number to gauge how many, like what proportion of them are false positives.
Yeah, because when I look at my like Manhattan plots, even if I do use the adjusted, the peaks are still the same kind of implications.
The Some people will just set the p-value threshold ridiculously low, just pick a tiny number, 0.00001 or something like that. Yeah, but if you want to I mean, this is statistical bioinformatics, so if you want to be specific about the level of confidence that you have in your results, just using p-values is not the answer, because then you can't tell me how confident you are in your results. If you did a Bonferroni correction, you'd find nothing, probably, because 100 and something thousand, you find a few?
Yeah, a couple hundred.
A couple hundred.
My peaks go like, so my Bonferroni says a lot of like 6, my peaks go like 20.
Mm.
So,
You could always do Bonferroni, and you could be extra confident that what you got is real.
but there's probably more.
There's probably more.
You're not getting.
Yeah. I mean, if you can find 100 something, maybe that's enough. Depends on how many you can afford to look at, you know. So at least you have an option. FDR is an option. It's used a lot because it is a little more liberal, I guess, in accepting errors. We're basically out of time. This is the picture we'll make next time. We're going to estimate stuff and estimate an FDR, and we will make a picture like this one. Estimated FDR. That's not the one I wanted. Yeah, that's what I wanted. This is like the picture part C from the paper. Estimated FDR, same thing as Q value, essentially. So error rate, how many features do I get? This one does not look like the one in the paper. The one in the paper had a nice peak spike, which made it kind of easy to say, okay, that's how much error I'm willing to accept. This one's much more gradual, and it's not as happy of a picture. But this is, again, what I would look at to decide what error rate am I willing to accept. I'll talk more about that on Monday. Questions? I'm going to assign the next homework assignment today, and it will be some testing stuff. So get a data set, do a t-test, get p-values, convert them to false discovery rates, make a picture or two. Will also be some cluster analysis, because we're going to talk about that soon, and then principal components and singular value decomposition and other exploratory techniques. Okay. Have a good weekend.